Okay, now let's talk about the case w equals 0, which is there's no damping term. Okay, I know like it is getting complicated, right? But like just try to just do your best to understand what I'm saying. Okay, so like the name of like this motion is like an undamped forced vibration. Forced vibration means like there is external force, but like there's no damping term. Okay, in the case is this guy. Okay, then like as you can see here, there's no by prime term, but like still we have like the like right hand side, which means it's non-homogeneous case. Okay, so but basically think about it, like if there is no damping term as we talked about in section 3.7, like the oscillation is just going forever as long as it's under damped motion, right? But like for these cases there's external force, and we can just simply consider like two cases. First one is like, think about it, the spring is oscillating right now, but whenever it is like when it is stretched out and you apply the force in the same direction, then what happened? Then definitely your oscillation is getting bigger, right? And actually that is the case too, right? Okay, your gamma is equal to omega, which means like the frequency of your original motion is same with external force. That means, as you can expect, whenever like your like spring is stretching out and apply a little bit more force, the same direction, then as you can see in this graph, like your oscillation motion is getting bigger and bigger and bigger. Okay, but what about the other case? Like your spring is like stretched out, but you apply the external force in a like an opposite direction, then your oscillation like is getting smaller. That is case number one. Look at that. Okay, and it's kind of like the natural vibration and your external force is against to each other. Okay, so like that's why like you can have like this kind of thing. Okay, we can say it is a bit. Okay, so that's it. Okay, so we can talk about a little bit more detail about this one with math. Okay, so here we go. Let me come back to the like differential equation. Okay, and like as you know, gamma is the forcing frequency, and then like omega is the natural frequency, which is noted by square root of k over m. Okay, we already derived whole this thing like before. Okay, then the first case, let's talk about your gamma is not equal to omega. Okay, then what happened? So basically, okay, we have to come back to the particle solution form. I'm talking about, where is it? We talked this a long time ago. I'm talking about this guy, okay? This particle solution, okay? And like, from this particle solution, we derive particle solution can be written by this way, right? But keep that in mind. It is undamped motion, which means like your B is 0. This B is equal to 0. Is it okay? Then your denominator is just like simply k minus m gamma square. Okay, let me rewrite this one on our page. So let me come back to the like undamped forced vibration form. Okay, my particular solution was f0 over k minus m gamma square and cosine gamma t, right? So like as we talked about, your omega is equal to k over omega is equal to square root of k over m, which means my k is equal to m times omega squared, right? When I plug it back into my particular solution, then my particular solution can be written by f0 over something. Oh, there was the square root here, right? Right? Omega squared minus m gamma square cosine gamma t. Okay, so like from this guy, we can write the solution for this case, okay, is equal to F0 over M times, let me factor that out, omega square, which is the natural frequency, minus gamma square, which is the forcing frequency, okay, times cosine gamma t. Is okay? This is particular solution form of the like undamped forced vibration K vibrations, which is case gamma is not equal to omega. Okay, and then whenever you have this one, when you draw the graph of this guy, and you can get like this kind of form. Okay, we're gonna say this is the bit. But look at this coefficient. Okay, like I'm talking about this coefficient. Okay, there's no t term, which means this is really like, just oscillating like with the same period and frequency and amplitude forever, right? So like that's why like your graph, like solution graph looks like that, just periodic. And the name of this one is bit. Okay. So now let's talk about another case, okay, which case your gamma is equal to omega, which means the natural frequency is equal to the forced frequency. Okay. As I told you, this is the case whenever your oscillation of your spring, whenever your spring is stretched out, you apply the force in the same direction, which means you make like bigger oscillation. Okay, so that is the case. Okay, so whenever you have this one, like since that your gamma is equal to omega, what happened? Your particular solution form is exactly the same with the corresponding homogeneous solution. Okay, so which means your particular solution must be like multiply t as well. Okay, and as we did before, we're gonna take the derivative, I mean like y prime, find y prime and y double prime and plug it back into the differential equation. Then you can get the particular solution form as like this one, F0 over 2m gamma t and sine gamma t. Is it okay? But look at this one, okay? Like actually we have like this part, okay? That is big trouble, okay? Does it make sense? Because like, like when you compare with previous one, like previous particular solution doesn't have like t term in the coefficient, which I mean like amplitude part, which means that you have like same amplitude, right? But for case two, since there's t on your amplitude, which is whenever t is increasing, your amplitude is also increasing. Does it make sense? And you can easily find that motion in the like in solution graph, okay, solution curve, okay, and we're gonna say that is a resonance.